All right, so this is the third example, and I don't like the fact that it's focusing the whole time. That's a little bit annoying. So I'm going to put this into still mode. I'll have it focus once. Hopefully it'll be okay-ish. So this is the third page of this. I'm going to work first of all on figuring out the total resistance of the circuit. This is a combined circuit. So if you note about that a little bit, what we've got here is a single resistor and then two resistors in parallel, and then another resistor all by itself. So I'm going to work first on simplifying this part of the circuit that's actually shown down here. So this 6 ohm resistor and 12 ohm resistor in parallel, I use the 1 over R1 plus 1 over R2 is equal to 1 over R parallel to figure out the total resistance in parallel. So that's 1/6 plus 1/12 equals 1 over that. So 0.25 equals 1 over the total, and so I get 4 ohms. And I can do that using the calculator that I talked about earlier. So 6 plus 12, and now that would equal 1 over the total resistance. So I've got to flip it again to get the total resistance. So this button is really important for what we need to use here with parallel circuits and combined circuits. So that's going to be 4 ohms. So now this turns into a circuit with a single 3 ohm resistor, an equivalent 4 ohm resistor, and a 5 ohm resistor. So now I can go back here and I can say that's basically a series circuit. So I can say the total resistance is equal to 3 plus 4 plus 5, and that's going to be 12 ohms. To get the total current, I'm going to use Ohm's law. I is equal to voltage over R total. So I've got 6 volts here, 12 ohms, is equal to 0.5 amps. To get the total power, it's V times I, so that's 6 times 0.5, so that's 3 watts. Okay, now I'm going to go and figure out things over here. So I know what A1 is already. I can think about how this is going to split down here in a bit, but I'm actually going to solve. Well, once again, I left out V1. That's the voltage of, actually, I don't know if I need V1. I'll do that anyhow. Oh well. So if I know the total voltage or the current in this circuit is 0.5 amps, I could say V1 is equal to I times R. Well, the current going through here is 0.5 amps. Resistance is 5 ohms. 2.5 volts. Now, thinking about the voltage here, I'm going to have for V3 0.5 amps, 3 ohms, 1.5 volts. Now there's a couple ways you can get V2, and we'll talk about that in a little, well, talk about it right now. So one of the ways is to understand that since the voltage across a parallel branch of a circuit is equal to the voltage across that whole component, the voltage I would have across here and the voltage across here would be the same as each other. That would also be the same as the voltage I could calculate across this equivalent resistance here. So if I could think of a voltage across this, I could say it's going to be the same as across here. Now there's a couple ways you could do that. One is you could simply take this, multiply it by 0.5 amps, and get the total voltage. So I could say V2 is equal to 0.5 amps. 4 ohms equivalent resistance is 2 volts. The other way I could do this is I could note that the whole voltage of the power of this circuit is 6 volts. And so I've used up 2.5 across here, I've used up 1.5 across here, and I end up that's a total of 4 volts used, which means since I've got to use the entire voltage up, no matter which path in the circuit I take, that means the voltage across this resistor would be 2 volts, and the voltage across this resistor would be 2 volts. It's not 1 and 1, because the voltage is basically the energy per charge that's used up, so that when the electric current gets to this junction, it can go either to the left or to the right. It can't go, any individual charge can't go both ways. And so essentially I've got 6 volts here, subtracting off 1.5 volts here, subtracting off 2 volts whether I go this way or this way, subtracting off 2.5 volts there, means I'm down to 0, which agrees with what I've got, which is a 6 volt potential difference. So I could say 6 volts minus 2.5 minus 1.5 will give me 2 volts left across this part of the circuit. So like I said, you could do that this way by looking at this equivalent resistance, or you could realize that the voltage that's left has got to be 2 volts. So now, once you know the voltage across these components of the parallel circuit, now we could figure out the current pretty easily. I could do that by saying 4 volts across this branch divided by 12 ohms in that branch would equal to 0.3 2 volts in that branch. Sorry. 0.167 amps. Now there's another way you could do this in just a moment. So here I could realize that the total current is 0.5 amps. If 1/6 or 0.167 amps went that way, 2/6 or 0.33 amps went that way. Or I could simply also do the V over R, 2 volts, 6 ohms, 0.333. The other way you can look at this is if you notice some symmetry here. We know that the voltage has got to be the same across here and across here, but the current does not have to split evenly, and it won't split evenly. Current is going to go preferentially to a path with less resistance. So this will have more current than this path will. How much more? Well, if I look at this, the resistance in the right branch is 12 ohms, resistance in the left branch is 6 ohms. There's twice the resistance in the right branch as the left branch, and so therefore twice the current will go in the left branch compared to the right branch. Why? Because the voltage would have to be the same. We know that voltage overall is equal to I times R. So I could think proportionally 2/3 of the half an amp would go here, 1/3 of the half an amp would go here. That agrees with what I got.